Okay, so we have seen that the three components of omega can be expressed as omega 1, omega 2, omega 3 in terms of the Euler angles, and we have seen that for heavy symmetric top we are working in a frame which does not include the psi rotation, the last Euler rotation explicitly. So, what we are doing here is we are setting psi equal to 0 to get the components of omega 1, omega 2, omega 3 for this particular axis, plus please understand that we are not putting psi dot equal to 0. So, we have these three components, and of course, we can write out the Euler's equations if we know the torque, right. So, in order to get the torque, let us start by writing n, which will be, okay. So, mg is working through center of mass downwards. So, we can write mg to be equal to mg k capped minus, okay. Sorry, it will be r cross mg. So, r is along the body z, which we also have not marked, okay. So, this will be our z axis, and let us call the three unit vectors as E1 capped, E2 capped and E3 capped, right. So, your r cross n will be equal to r cross f is mg minus k capped, which we just wrote, and r is equal to h E3 cap. So, we have h E3 cap cross mg k capped, k dashed cap with a minus sign. So, the minus will come here. Now, as we have not taken the third Euler rotation into account, this has a significance, because it makes the mathematics so simple in this particular formalism. See, one thing we can do is we can also write, we can okay, let us talk about it later, because right now no point. So, if we take psi is equal to 0, then my x axis, the body x axis lies in the x prime y prime plane. That means, it is in the plane of the space xy, right. In that case, we can decompose this k3, which is so if I mark them as I or k prime, sorry, not k3, k prime, I prime, j prime and k prime. So, in that case, we can decompose k prime in terms of E3 and E2, right. So, we can write k prime to be equal to k prime dot E1 capped plus k prime dot E2 times E2 plus k prime dot E3 times, sorry, E3 times E3. Okay. So, we can do that, and we see as the E1 is always perpendicular to k, because it is in the xy plane. So, the first term is unanimously equal to 0, whatever may be the value of phi, okay. And if that is the case, then you see that this can be decomposed in this body yz plane, and we can write by considering this angle theta. In terms of this angle theta, we can write this as, so the first will be E2 is the y is sin theta, right. So, we have sin theta E2 capped plus cos theta E3 capped, right. So, when we put this back in the expression of n, what we gain is minus, what we get is this mgh, okay. So, E3 cap cross sin theta E2 capped plus cos theta E3 capped. Now, once again the last term will vanish, because the last term is a cos theta E3 cap term. I hope you can see this. So, last term is cos theta E3 cap term. This will vanish because it has E3 in here, right. So, only the surviving term will be E3 cross E2, which is minus E1. There is a minus sign here, okay. So, this will give you m g h sin theta E1 cap. So, n is this. Also, not considering psi into account, I mean putting psi equal to 0 explicitly has another significance when we look at it from the space set of axis. So, from the space set of axis, your torque will be, okay. So, if we try to compute the torque will be along, so the expression of torque will be the same. So, it will be E3 cross mg k capped, right. Now, this is important. Without decomposing it into this components of E2, I mean without decomposing k prime into E2 and A3, we can see that the torque is a cross product. I mean it has to be always perpendicular to k prime, right. So, it could be anywhere in this xy plane. If we look at it from the space set of axis, please try to understand x prime, y prime, z prime, as n is equal to this something cross k prime, that means the torque wherever it is can not be along z prime axis, okay. So, the torque, if this is the expression of torque in the space set of axis. Now, in the body set of axis. Now, in the space set of axis, n can have a general form of n1 I capped plus n2 j capped. Because the k capped comes in the expression of n itself, this can never have a component in the z direction. Now, this has a significance, we will see later. Now, we have this mathematics worked out. Next is writing out the Euler's equation. So, of course, we can write out 3 Euler's equations explicitly, but the first and second Euler's equation we will not do. I mean, we will not write the first and second Euler equation. So, the first equation will be some I1 omega 1 dot plus something equal to N1, which will be mgh sin theta E1, E1 cap we do not need. Similarly, second Euler equation will be I3 omega 3 omega 2 I1 omega 2 dot, because I1 is equal to I2 and we have I3. So, we will just write I1 and I3. We will not write I2. The second equation is also this plus something equal to 0, but the third equation is something that we will write out explicitly. It will be simply I3 omega 3 dot is equal to 0. So, I am leaving it to you as an exercise why this will come once we put psi equal to 0. Okay. So, you will see that this exactly is going to happen. I mean, of course, you do not even have to put psi equal to 0. The third equation will take this form because the torque is 0 and I1 is equal to I2. So, from here we can get omega 3 is a constant. And what was the expression of omega 3 we have taken? We have written omega 3 as phi dot cos theta plus psi dot. Okay. So, this is a constant we see immediately from the third equation. This is the first, this is the second, this is the third. So, I am not writing the first two explicitly because we are not using it. Okay. So, the idea is the following. We will not try to integrate these equations. This could be integrable, definitely they are integrable. We are not trying to do that. Although omega 1 and omega 2 they are written out explicitly in terms of 3 Euler angles phi, 2 Euler angle phi and theta, and of course we have psi dot which is the spin into account. We are not trying to integrate it for heavy symmetric top. Instead, what we are going to do is we will try to find out what are the conserved quantities we have, okay, and we will write, we will try to give a quantitative description of the motion based on the functional form of certain parameter we will get. So, this is the strategy we are going to follow. Okay. So, this is, so essentially we will see that there are three conserved quantities we can write out. One is A, and again when we will be dealing with Lagrangian dynamics, we will revisit the problem of symmetric top, and there we will see that these conserved quantities are nothing but associated conjugate momentum to certain momentum which are supposed to be conserved, by which we will which will be obvious from the Lagrangian of the system. But right now let us just look at the conserved quantities we are getting. So, one is this quantity which we call A. Now, look at this once again. There is no component, when we look from the space set of frame, there is no component of torque along Z. So, if let us say if this is your space Z, which is Z prime, and let us say this is your angular momentum L. So, angular momentum, because there are torques in the xy plane, so let us say this is the general direction of the torque, which is N1 plus N2 in the xy plane. So, angular momentum will change in the xy plane, but as there is no torque in the xy plane, in the z axis, the projection of angular momentum along z axis, which is L dot, sorry, not z cap, this is k cap, equal to a constant. It has to be. That is from the physical point of view, because please remember angular momentum can change. I can from space set of axis, from space set of axis, our equation is simply dl dt equal to n. Okay. So, I can decompose it into dl1 dt equal to n1, dl2 dt equal to n2, and dl3 dt equal to n3. So, if n1 is equal to 0, we can immediately tell you, or sorry, if n3 equal to 0, then we can immediately tell you that L3, which is equal to a constant, and L3 is nothing but L dot k prime. That is written out in the space set of axis, right? Okay. Now, so this will be another conserved quantity k prime, sorry, right. Now, L, okay, so L is I1 omega 1 plus I2 omega 2 plus I3 omega 3, that is written out in body principal axis, right, that we have seen. So, we can take L, okay. So, this is one expression which we can use. I mean, does not matter if we write the vector in this frame or that frame, this is something which we can use, right. So, L dot k prime is L dot, and if you recall, we have already decomposed this into E1, E2, E3, the k prime we can write in terms of E2 and E3. So, if we simply use this expression and write sin theta E2 plus cos theta E3, right, and so only these two components will survive, the first component will not contribute. So, it will be I2, or I will write I1 because we are writing I1 and I3 only. So, it will be I1 omega 2 sin theta plus I3 omega 3 cos theta, and you recall that omega 3 is a constant which is A. Okay. So, if we call this whole thing equal to some constant k, then we can say k is equal to I1, and omega 2 is phi dot sin theta, right, plus I3 A cos theta is equal to k. So, we have our first conserved quantity here, which is A, which we have our second conserved quantity here, which is k. K is the capital K. Okay. two conserved quantities are already there. Now, it turned out that turns out that for this particular system, the torque, the force, applied force is not a function of time, okay, because it's a mass. Of course, it's changing with mg cos theta, but there is no explicit time dependence into this force. And if there is no explicit time dependence, it can be proved that the energy of the system is conserved. Once again, there are proofs, there are classical proofs available from Newtonian mechanical side, or also we can use Lagrangian dynamics to prove it. But it's not terribly important. I think we will all agree to the fact that the energy conservation is valid. So, we can write E equal to, which is a constant, and E can have two parts, one have kinetic energy and one have potential energy. Potential energy part is simple. We can just write potential energy as mg h cos theta. Look at this picture and you will agree to that. Okay. So, if this is mgh, so the height is essentially L cos theta, right. So, h cos theta. So, this vertical height of the center of mass. So, the potential energy is mgh cos theta. Now, for the kinetic energy, please recall kinetic energy T is given by half I omega square, and if we, or which is equal to half omega square n I n. Now, if we resolve it in the remember our discussion on ellipsoid of inertia. So, when we resolved this n dot I dot n in a principal component, or principal frame of reference, all the cross terms vanished. So, in that particular frame, the expression for T will be simply half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square, right. Now, omega I1 and I2 are equal. So, the first term will be simply half I1. Now, putting the expression for omega 1 and omega 2, it will be theta dot square plus phi dot square sin square theta, right. So, this is the expression for omega 1 and omega 2, and for omega 3 once again we can put A. So, the third will be A I3 I3 square. Now, this is the expression for kinetic energy. If we write it for total energy E, so we just have to add mgh cos theta to it, and this term is also a constant, okay, that we all know. And total energy, so we have three conserved quantity, one is this A, one is the K, and one is U. Now, it turned out that we can also write this part in terms of K. Please recall that K is given by this particular expression, okay. Of course, we have not right. So, in the second expression, now we can start our manipulation. What we are going to do is, we are writing E. So, I am using a different color of ink, because now what we are trying right now, so far what we have done are simply, we have simply written out the expressions. We have not done any mathematical manipulation. Now, it is time that we start our mathematical manipulation. The first one is by writing IE, which is half I1. See, theta dot square stays theta dot square, plus what we are going to do is, we are going to write phi dot square sin square theta in terms of K and A. So, if we do that, it will be K minus I3 A cos theta by cos theta whole square by 2 cos theta whole square by I1 square sin square theta. Check the expression of K and this will be obvious to you, and then this one stays as I3 square plus mgh cos theta, okay. So, this bracket will close here, right, okay. Now, let us put u equal to cos theta. Do not mix it up with u equal to 1 by r, we are not doing central orbit, it is just some some notation, u equal to cos theta. So, u dot is equal to minus sin theta theta dot, and sin square theta we can write as 1 minus u square, right. So, whenever we get cos theta, we can call it u, for example here. Whenever we get a sin square theta, like here, we can call it 1 minus u square, and we have an u here as well, right. And of course, you have u dot. So, once we do that, see, u dot has a theta dot term in it. So, theta dot, what we have here, can be said to be u dot minus u dot by sin theta, and theta dot square will be u dot square sin square theta. Sin square theta once again is 1 minus u dot. So, doing this mathematical jargon, I mean, it's just some juggling, algebraic juggling. It's what we are doing here is pure algebra. We are not going to do differential calculus. Although the equations we started with is Euler's equation, which we did not use explicitly. Okay, by the way, this expression of k can also be derived by writing first, if I write to first to Euler's equation explicitly, then from there it can be shown that this 2 can be used to write dk dt equal to 0, which is worked out in classical mechanics by Spiegel. You can have a look at it. So, if I, instead of doing this physical pictures thing where we write it, I mean, we try to analyze L in terms of the space set of axes, we could have done this mathematics also, but I like the physical picture. So, that is why I did it this way. Okay. So, of course, we are not writing the Euler's equation explicitly. Instead, what we are doing is mathematical manipulation, and it turned out to be pure algebraic in nature. Right now, we are not writing a single differential equation. We are just doing pure algebra. Of course, if you call that, there is a u dot here, I mean, it's, if you call it, okay, it's differential calculus, then we are doing differential calculus. But in my opinion, it's pure algebra. Now, keep doing it, and essentially you can rearrange this entire equation. I am not doing it for you, you can do it yourself. Two steps in mathematics as k minus I3a by I1 whole square u square plus 2mgh by I1 u 1 minus u square plus okay, so it will be 2 by I1 half I3a square minus e whole times 1 minus u square equal to 0. So, this is what we can get from this. Now, it is time to define some constants alpha, which is equal to let us say alpha will be what? Okay, let us start from the last one. So, if I take this 2 up here, this 2 will cancel out. So, let us call alpha to be equal to I3a square minus 2 I3a square minus 2e by I1. So, there is an I1 here. So, let us call this alpha. Let me see. Yeah. So, this will be your alpha, and there is an u1 minus u square here, right. Beta will be equal to 2mgh I1, this part. Gamma will be equal to k by I1, which will come here, and delta will be equal to I3a by I1, which will come from the second term. So, if we substitute this, we can once again do a slight little bit of mathematical manipulation, and we can write this whole thing as 1 minus u square alpha minus beta u minus gamma minus delta u whole square, and this is a function of u only. So, in this expression alpha, beta, gamma and delta all are constants. So, the only variable is u. So, we can write this f of u. Now, it is u dot square equal to this. So, we can also try to integrate that. Now, also there is a second expression. If we start with the expression of k and try to write this expression of k by in a slightly modified form in terms of all this newly introduced parameter alpha, beta, gamma and delta, then we can figure out that phi dot is equal to gamma minus delta u times divided by 1 minus u square. So, these two are the expressions which we will be using to give a physical description of Topp's motion. Now, if we try to integrate this equation, the first equation, second equation also we can integrate in principle. So, if we try to integrate these two equations, what do we need to do? If take the first equation, which is f equal to fu, which will be integrated to give dt equal to integration dt is equal to integration du by root fu, right. So, in principle this will give you u, which is equal to cos theta as a function of time, okay, u as a u of t. So, that means essentially by solving this you get theta as a function of time. Now, plug it back into the second equation, which is phi dot is equal to some another function of u, which is actually this, okay, which is some function of u, right. And now, once you get u equal to u in theta in terms of t, so you can substitute, you can define a new function which is p prime of t by substituting the u here, right. So, essentially this can be integrated to give phi, which will be integration of p star t dt. Sounds simple, but as I said during the discussion of central orbit, we can in principle also integrate in a similar manner. We can integrate r and theta to gain, to get the complete description of the orbit in terms of as a function of time, but we don't do that. We don't do that frankly because it's very, very hard, and this is also a very difficult integration. The first integration itself, it's an elliptic integral. There is a class of integral which are called elliptic integral, which are extremely difficult to execute. Look at the functional form of u dot. It's not so easy. Also, it might not be possible analytically, but numerically it might be possible. Of course, people can do that, but also this is not strictly needed. What we are aiming at is essentially we are trying to gain a physical insight of top motion by not solving any equation. We just want to see how it works, okay. So, for that we need to, in strictly speaking, we can just stick to these two equations. We try to examine the functional form of fu quantitatively and we will gain that insight. So, let us start in that line. F of u, see, I am not writing the expression, okay. So, let us write the expression once more. F of u is equal to 1 minus u square alpha minus beta u minus gamma minus delta u whole square, okay. So, what is the leading term in this? The leading term is this, which is beta u cubed, and then we have, of course, there will be a gamma u squared term and all. So, it is a u cubed, the leading term is alpha u cubed and it is a polynomial, okay. So, now if it is a polynomial in nature which goes with the leading term of u cubed, so that means as u goes to infinity, f of u goes to infinity in the positive side, as u goes to minus infinity, f of u, because it is an odd function, u cubed is an odd function, right. So, f of u also goes to minus infinity, right. So, if we try to draw a quantitative description of it, then And also if you please understand that if you put u equal to plus or minus 1 in this expression, so both case first term will definitely vanish. Okay. So if the terms vanish at u equal to 0, if you put u equal to 1, so f of u will be some number, right. So u equal to 1, so f of u will be minus gamma minus delta, u is equal to, sorry, if you put u equal to plus minus 1, u equal to plus or minus 1, both cases the first term will vanish because it is 1 minus u square, and the second term will be minus of gamma plus or minus delta whole square. Now, does not matter if this gamma plus delta or gamma minus delta is negative, the square will always be positive. So, at u equal to plus and minus 1, f of u is negative definite. So, we have three condition on u, that at f equal to u equal to infinity it goes to plus infinity, u equal to minus infinity it goes to minus infinity, and at plus and minus 1 it is negative definite. Now, if I try to plot f of u, so you have f of u, this is your u axis, this is your plus 1, this is your minus 1. So, we can say that it is going to minus infinity, it is going to plus infinity, and in this case, these two cases it is negative definite. So, some point it has to cross 0. Okay. So, we can have the following trends, we can either have it like this, or we can connect it like this, right. So, there are two ways, either this is my path 1 and this is my path 2, two possibilities of u, I mean two possibilities in which f of u can behave between minus 1 and 1. We can stay in the negative direction or it can go to 0, positive and come back to negative. Okay. So, this is where we stop now, and we will come back in the next lecture. We will start from this particular picture and see which one gives you a physically possible motion. From there we will go ahead and see what are the possible physical picture of the top motion we can extract from this continuing on this particular line. Okay. And then we will end this discussion of symmetric top or discussion of rigid dynamics with two special cases of slipping top and